Welcome back to our lecture in Geotechnical Engineering with the topic Compressibility of Soil. A stress increase caused by the construction of foundations or other loads compresses soil layers. Yes, that happens. Compression of soil layers happens when there is a force or load that exists on top of it. The compression is caused by, the first one here is the deformation of the soil particles. The second one is the relocation of soil particles. And the third one, expulsion of water or air from the void spaces. So let's take the first one. So deformation or the compression happens because of deformation of soil particles. So how does the deformation of soil particles be the cause for compression? So let's take this as the volume of a soil sample. So this is our soil sample, and in this volume of our soil sample, we have the soil particles plus the spaces or the voids that exist in this sample of height h. So if this sample of soil experiences load on top of it, so there is a load P on top of this, what happens here is compression due to the deformation of soil particles. So for example, it flattens out like this, like a pancake. So it flattens out. Thus, in this volume of soil particles, there exists a change in height. So this change of height is our settlement or the compression of the soil layer. Okay? So this is due to deformation of the soil particles. Now, the second one is the relocation of soil particles. So, why does relocation of soil particles cause compression? So again, let's have here a soil sample of a given volume. So, these are the soil particles. Okay? So, in this volume of soil, same with the first one here a while ago, contains solid particles and voids here, voids which contains air, water, etc. Okay. So in our second cause of compression, it says the relocation of soil particles. So upon introducing a force P on top of the soil layer of height h, there exists a relocation of the soil particles. So in this volume, the soil because of the force, the soil particles find or some of the soil particles start to look for void spaces on its neighboring area and start to fill it. Thus, these soil particles are removed from the soil sample. So there causes a delta H or the settlement, a change in height, or then the existence of the compression. Okay? So the soil particles are relocated, but if you notice, there still exists voids in this soil sample. So voids are still in there, but some of the particles have relocated. Now the third one is expulsion of water or air from the void spaces. So let's take again an example, a volume of a soil sample here of solid particles, containing solid particles and voids. So we have here height h. If we expose this soil sample on a force P, what happens here is the removal of the void spaces. It becomes denser because the content of solid particles are still there, so there is no expulsion of solid particles. The only ones that has been expelled are the voids, the water. What I mean is the only thing that has been expelled is the water or air from the void spaces. So this becomes denser and a delta H or settlement occurred or compression occurred. Okay. So these are the causes of compression. So in general, the soil settlement caused by loads may be divided into three broad categories. The first one, we have the elastic settlement or the immediate settlement with the symbol S sub E. The second one, we have the primary consolidation settlement with the symbol S sub P. And we have the third one, secondary consolidation settlement with the symbol S sub S. So let's differentiate these three. The first one, we have the elastic settlement or immediate settlement. So you can notice here elastic and immediate words. So what do we mean by elastic settlement or immediate settlement? It is caused by the elastic deformation of dry soil and of moist and saturated soils without any change in the moisture content. Elastic settlement calculations generally are based on equations derived from the theory of elasticity. Elastic or immediate settlement of foundations S sub E occurs directly after the application of a load without a change in the moisture content of the soil. The magnitude of the contact settlement will depend on the flexibility of the foundation and the type of material on which it is resting. So why is it like that? Well, let's go back to the definition of elastic deformation. What do we mean by elastic deformation? So when we say elasticity, it is the ability of a body to resist a distorting influence and to return to its original size and shape when that influence or force is removed. Okay? So meaning, it is a temporary settlement because it can go back to its original size. And it's also notable that this is the first settlement that we can observe in a soil layer because of the word immediate settlement. Okay? So this is the settlement that is noticeable in a short period of time. For example, if there's an area, your construction site, you load it up with piles of steel bars, so that soil area experience the first settlement, which is the elastic settlement or the immediate settlement. So it experiences change in H, which in some time, if you remove that load, for example, that pile of steel bars, if you remove those loads, there's a possibility of the soil layer to return to its former shape or to return to its former height. And then that delta H can become negligible. But still, it is noteworthy to compute for delta H for determining the settlement on that area. Okay, so the first that we are going to solve is the immediate or the elastic settlement. Next, the primary consolidation settlement is the S sub P, which is the result of a volume change in saturated cohesive soils because of expulsion of the water that occupies the void spaces. So here, the void spaces has been reduced because of the expelling of the water and air. Okay, so here in our primary consolidation settlement, this comes right after immediate settlement, because if the loads are left there for a longer period of time, the voids can be removed. Okay, so the voids can be removed. Number 3, secondary consolidation settlement, symbol S, the S sub S, which is observed in saturated cohesive soils and organic soil and is the result of the plastic adjustment of soil fabrics. It is an additional form of compression that occurs at constant effective stress. Now, take note of the word plastic adjustment. So what's the difference again between elastic and plastic? Okay, so elastic is temporary. But when we say plastic, okay, the material will experience permanent deformation. Okay, so in this settlement, this kind of settlement, the soil layer experiences a permanent deformation. Okay. So this happens when the load that is being experienced by the soil layer or by the soil is happening over an extended period of time. So in this third category, we will incorporate the parameter time to experience the plastic adjustment of soil fabrics. Okay, so we have these three broad categories: the elastic settlement, the primary consolidation settlement, and the secondary consolidation settlement. If you add them up, that is the total settlement. Okay, now let's go to the formulas for these three categories of settlement. The first one, the elastic settlement or the immediate settlement. So the formula for elastic or immediate settlement is S sub E is equal to CS small q B times 1 minus mu squared over E sub S, and that is also equal to I sub P QB 1 minus mu squared all over E S or E sub S. Okay, I do hope I pronounced this correctly. Okay, for the C sub S, that is our shape and foundation rigidity factor. The I sub P is our influence factor. We have small q as the net vertical pressure, and we have here the formula Q is equal to P over B squared, where P is the load and B is the width or diameter of foundation. And then this mu here is the Poisson's ratio, and then E sub S is the modulus of elasticity of soil. Okay. The second one is the primary consolidation settlement. We have two basic definitions of clay based on stress history. We have the normally consolidated in which OCR is less than 1. And then we have the second one here, the over-consolidated, where OCR is greater than 1. Okay? So this first one here, we have the normally consolidated, wherein OCR is less than 1. So what is OCR? Okay. So OCR is the over-consolidation ratio. Okay. Then over-consolidation ratio is equal to P sub C over P sub O. What is P sub C? P sub C is pre-consolidation pressure or stress. P sub O is the initial effective stress at mid-height of clay layer. It is also called the overburden effective stress. Then we have the formula for the settlement, primary consolidation settlement. S sub P is equal to H over 1 plus E C sub C log of P sub F over P sub O, where H is the thickness of clay layer, E is the void ratio, C sub C is the compression index, and we have formula for compression index. We have 2. Okay? So the first one, is C sub C is equal to 0.009 times liquid limit minus 10. And this formula is for the undisturbed clay. The second one, we have C sub C is equal to 0.007 times liquid limit minus 7, and that is for remolded clay. Okay? So that's the formula. And then we also have here C sub S, the swell index. That is 10% to 20% of C sub C. And if it is not mentioned, then you can use 20% C sub C. If it is not mentioned, let's take the maximum there. Then we have here the P sub F. P sub F is the final vertical effective soil stress. And this P sub F here is equal to P sub O plus delta P. So that's why here in our third formula here, we have S sub P is equal to H over 1 plus E C sub C log of P sub O plus delta P over P sub O, wherein delta P is the effective stress increase. Okay? So in order to fully memorize and understand this, we will solve sample problems later on. Next, the letter B, we have the over-consolidated wherein OCR is greater than 1. So over-consolidated, whose present effective overburden pressure is less than that which the soil experienced in the past years or in the past. The maximum effective past pressure is called the pre-consolidation pressure, okay, or P sub C. So we have there the P sub C, pre-consolidation pressure or stress. So we have another 2 cases here. The first case here is when P sub O is less than P sub C and P sub C is greater than the P final. Remember, this is the P final, or that is P sub O plus delta P. If that satisfies our condition, or if that condition has been satisfied, then use this formula. S sub P is equal to H over 1 plus E C sub S log of P sub O plus delta P over P sub O. And again, C sub S there is swell index. Okay, we have the second case. We have the P sub O, or the initial effective stress, is less than the pre-consolidation pressure or stress. And that pre-consolidation pressure or stress is less than the P final, or the P sub O plus delta P. And if this case here has been satisfied, the situation there, then this is our formula. S sub P is equal to H over 1 plus E multiplied with C sub S log of PC over PO plus C sub C log of PO plus delta P over P sub O. Let's go to the third one here. We have the secondary consolidation settlement. Again, if you recall, this is our plastic deformation. This is the temporary one. And we need time to have a permanent, permanent. Okay? So we need time to have a permanent settlement. So that's why we have the formula here. S sub S is equal to H over 1 plus E sub P times C sub alpha log of T sub 2 over T sub 1. Wherein C alpha is the secondary compression index, T sub 2 time after completion of primary settlement, that is in years. T sub 1 time for completion of primary settlement in years. So T sub 2 is after the completion, and then T sub 1 is for the completion. E sub P is the void ratio at the end of primary settlement, and here is the formula. E sub P is equal to E sub O minus delta E, where E sub O is the initial void ratio, or the void ratio before the vertical load is applied. And we have the formula for delta E here as C sub C log of P sub O plus delta P over P sub O. Calculations of consolidation settlement under E foundation. So we can use this to approximate actually. Average increase in pressure below the center of E foundation. Delta P average is equal to delta P sub T plus 4 delta P sub M plus 4 P, that's plus delta P sub B all over 6. Okay, so that's my pigs. Okay, so that's formula for the average increase in pressure, wherein we have delta P sub T is the increase in pressure at the top of the layer, and then we have there the delta P sub M, that is the increase in pressure at the middle of the layer, and then delta P sub B, increase in pressure at the bottom of the layer. Okay, so that's for the formula. Let's answer the sample problems. So I have prepared 5 sample problems, and let's try to solve them one by one. Okay, so there are formulas that I wasn't able to mention, but you can have it from our sample problem. Number 1, when the total pressure acting at the mid-height of a consolidating clay layer is 200 kilopascal, the corresponding void ratio of the clay is 0.98. So if we write that one, the total pressure acting at the mid-height of consolidation layer is 200 kPa. So for letter A, we have PI, or maybe let's put it first. PI is 200 kilopascal. The corresponding void ratio of the clay is 0.98. So at P1, E sub 1 is 0.98. When the total pressure acting at the same location is 500 kPa, the corresponding void ratio decreases to 0.81. So that is 500. Then E sub 2 is equal to 0.81. Okay? Letter A, compute the compression index. Letter B, compute the void ratio of the clay if the total pressure acting at the mid-height of the consolidating layer is 1000 kPa. Letter C, compute the compression or compute the coefficient of compressibility. So for letter A, we have there the compression index with the given P and void ratio. So C sub C is equal to E sub 1 minus E sub 2 all over log of P sub 2 over P sub 1. Okay, so that's the formula. Okay, so that we will just substitute the values. That is equal to E sub 1 is 0.98 minus 0.81 all over log of P sub O of log of P sub 2. So that is log of 500 all over P sub 1 is 200. So to compute that, we have the final answer 0.427. And it is unitless. Now let's go to letter B. Letter B is compute the mid-height or compute the void ratio of the clay if the total pressure acting at the mid-height of the consolidating clay layer is 1000 kilopascal. Okay? So it's looking for the void ratio. Acting at the mid-height of the consolidating layer. So let's take the answer here because it means that it is the CC for the difference of E sub 1 and E sub 2. So let's put here 0.427 equals our E sub 1 there is 0.98 minus E sub 2. Then we have here log of the pressure experienced. So this is 1000 over the original one, we have 200. So that is equal to, so E sub 2 is equal to 0.68. Next, number 3, or letter C. Compute the coefficient of compressibility. For coefficient of coefficient of compressibility, we have the formula A sub B equals delta E all over delta P. Okay? So our delta E is just the difference of the two deltas. So, or the two E, the two void ratio. Okay, so that is 0.98 minus 0.81 all over 500 minus 2,000. So that is equal to 0.00057 square meter per kilometer. Okay, so screenshot first for the problem number 1. Let's go to the example number 2. A normally consolidated clay layer, 3 meters thick, has a void ratio of 1.1. So, the layer is 3 meters thick, or that is 3,000 mm. So, if I take that, then we have the void ratio E is equal to 1.10. Liquid limit is equal to 40. Then we have there the average effective stress on it is 80 kilopascal. Average effective stress delta, or no, that is P sub O. The average effective stress, so P sub O, it is 80 kilopascal. Then the average stress on it is increased by 120 kPa as a result of the construction of a foundation. So that is our P final. Our P final is delta, or that is, let's start with P sub O plus delta P. Okay. Where is so the first question here is compute the consolidation settlement that the clay layer undergo. So we have 3 broad categories a while ago. We have the elastic, the secondary, and the primary settlement. So which among those formulas are we going to use? So we cannot use the secondary because there's no time given in the problem. Okay. So eliminated for the secondary consolidation settlement. How about the elastic? You can also eliminate that because of no presence of small q here and the Poisson's ratio. Therefore, we can conclude that we are going to use the normally consolidated. So we will be using the primary consolidation settlement. SP. And the formula for SP is, let's take the formula. We have the H over 1 plus E 100. So SP is, we have the H, it is 3000 mm all over 1 plus 1.10 and it's our CC or CS. Okay, so we have here the CS of 0.20% of CC. So our P sub O, how is our P sub O, delta P, and okay, so given PO, we have our delta P plus P sub O. What else? PC. So we cannot compare it here. So there is no mention of pre-consolidation. Okay. Therefore, we are going to use, since there is no mention for P sub C, we can then conclude that this is the one being used. So SP 3000, or I should write the formula first. So S sub P is H over 1 plus E CC log, so CC log of PF over P sub 0. So let's see if we did it right. Okay, so we did it right. Now what else is, we need to have the value of C sub C. And from this problem, the soil here is an undisturbed soil layer. So if it is an undisturbed clay, therefore it is 0.009 times LL minus 10. So if it is undisturbed clay, then we can now compute for C sub C. So C sub C is equal to 0.009 LL minus 10. So 0.009, liquid limit given 40 minus 10, that is equal to 40 minus 10 is 0.27. So we now have SP, S sub P is equal to 3,000 all over 1 plus 1.10, 0.27 log of delta, so P delta here, so it becomes 120 kPa. So it's the average stress on it is increased to 120 kPa. So that becomes P final, P sub O plus delta P. So log of 120 all over P sub O, 80. So S sub P is equal to 3,000. So 3,000 over 2.1 times 0.27 log of 120 over 80. So that is equal to 67.92 millimeters, because we have here the 3 meters becomes 3,000 millimeters. Okay, let's go to letter B. For letter B, if the clay layer is pre-consolidated, compute the consolidation settlement if the pre-consolidation pressure is 96 kilopascal. So this time, PC is given. So PC is 96 kilopascal. And if PC is given, we won't use the normally consolidated clay. We will have the over-consolidated. So we will check which among these two cases fits. Okay. So our P sub O is 80. So P sub O is 80. Our PC is 96. And what else? We have P sub O plus delta P. So P sub O plus delta P, that is 120. So this is, which one? P sub C is greater than PO but less than PO plus delta P. So this is the case, the second one. Therefore, we're going to use this formula. So S sub P, so S sub P is equal to the formula H over 1 plus E, and then we multiply it with CS log PC over PO plus we have CC log of P final over P sub O. So this P final here is P sub O plus delta P. Okay. So this is 3,001 plus 1.10 times CS of, again, what is CS? So, let's take the maximum. So, let's put CS here. Maximum, that is 10% to 20%. So this is 20% of CC is equal to, so what is 0.2 of C sub C of 27 or 57? Oh, that is CC 0.27. So 0.2 times 0.27 is 0.054. So CS here is 0.054 log of 96 over 80 plus CC of 0.27 log of 120 over 96. So that is equal to 43.5 millimeters. Okay, so that's for letter B. Next, letter C. Letter C here is compute the consolidation settlement if the pre-consolidation pressure is 130. So PC is 130. So we have PO of 80, PC of 130, then PO plus delta P is 120. So this is P sub C is greater than P sub O and P sub O plus delta P. And that formula or that scenario is okay, so this one, and the number 1, so for C sub C, for letter C we have here SP is equal to H over 1 plus E C sub C, C again, C sub S. Okay, so that is C sub S log of P final over P sub O. So that is equal to 3,000 over 1 plus 1.10 0.054 log of delta P sub 0, the P sub 0 or P sub O plus delta P, that is 120 over over P sub O is 80. That is equal to 13.58 meter or mm.